Hello class. Today we have our lesson on limits. Now with limits we are going to start off with our to-do, and on this to-do we're going to go with graphing the function f of x is equal to 1 plus 1 over x, and this whole bit here is raised to the value of x. After you've done that, I want you to begin on this question after you have your function graphed. So feel free to pause the video at this time to do this. So I hope your graph looks similar to mine. Here I use Desmos to end up graphing this function. And if you see here, I also have a data table. This data table can be claimed in Desmos by simply pressing this settings button and selecting the data table. What's handy about this system here is I can actually plug in values here for my input, so negative 0.5, negative 1, 0, and get my output. And if you notice, these are undefined, stating that in this area here, I do not have a value for my f of x. But we also notice that as our x value increases, as we're going down and it starts getting larger and larger, we're beginning to approach the same value. And similarly, on the other side, as we approach the negative larger numbers, we also approach the same value, which is here, e. If you remember when we were discussing e with compound interest, this is actually the function that talks about how we actually can solve for the value of e. As a reminder, this function here, f of x equals, not now, equals 1 plus 1 over x raised to the x. This can also be written simply as a sequence. Remember, we can plug in saying that x is some count, and that f of that count here would be equal to some term. So in changing our view here, we're going to consider this function as a sequence now. And if we consider it a sequence, that means we have to consider starting our count from 0. So we only count the positive end of the axis. Okay? So using those values, let's handle this question, saying question 3, what is the value for, or of f of x as x approaches infinity. That's a terrible infinity sign. Let me redraw that. There we go. Now, notice that I say approaches infinity and not saying it is infinity, because infinity here, this is a concept. It is not a discrete number, nor is it finite. So please keep that in mind. So to answer this one, we have to look at, as x goes down this number line and becomes increasingly larger, as it approaches infinity, what does f of x approach? Well, f of x is going to be equal to e. As x becomes larger, f of x just becomes closer and closer to the value of e. So we can simply say that as x approaches infinity, f of x equals e. So how does this relate to the lesson on limits at all? Well, limits refers to what limit you're approaching in your function. So I can actually rewrite this as the limit, doing a little bit of cursive here, just force of habit, as x approaches infinity. This is the notation here, saying the limit up here as x approaches infinity. And here you just write in your function. So our function is, you could write that as f of x, or you can actually include the function, which it would be 1 plus 1 over x, all raised to the value of x. But you also have to rewrite your limit. And actually, with limits, you can shorthand limit to be LIM. And I will continuously do a cursive. Actually, I think cursive here is LIN, so I have to add one more hill. So this would actually be your limit, and what is it equal to? Well, it's equal to e. So both of these in this case are equal to e. And that's the notation for this. So actually, here, when we had f of x equals e, that's not our real notation. This would be our real notation down here below to say the limit as x approaches infinity for f of x equals e. And if I want to write out what f of x is equal to, I would throw this in. And typically we would use the bottom here. Let me just circle that. We would use the bottom here as our correct notation. So let's go through some more examples. So here we have a new problem. This example 1 states, what is the limit as n approaches infinity? Now notice I'm using n as our variable here. Any variable can be used so long as you note that you have another variable in the actual problem that you're changing and approaching infinity. So we have this constant here, 1/2, is being raised to the n. So as n approaches infinity, what is this whole thing equal to? So take your moment to try and think how you would approach this. Alright, stumped yet? Well, here's a good way that I would approach this. I would just simply set up a graph. And start by saying that here, let's make this 1, 2, label your axes, 3, 4, and just make it 5. That should be enough. And what's the value as n is equal to 1? Well, you're going to get 1/2. So let's just put this up here. This is our half point. And that's 1/2, so 1 and 1/2. And the next one, 2, would mean it's 1/4, right? So it'd be halfway down, approximately 1/4. Again, I'm just estimating freehand the sketch. And 3 is going to be 1/8, half away on that. And you can feel free to graph this on your calculator if you like, but I'm just showing you the trend here, because actually as you go further and further down this line, you're going to notice that as x approaches infinity, we note that actually it's approaching this horizontal axis, or in this case, it's approaching a value of 0. So in this case, we can say that this value here is actually 0. So for this one here, as x approaches infinity, sorry, n, my apologies, I keep saying x. As n approaches infinity here, wrong one, as n approaches infinity, for 1/2 raised to the n, we get a value of 0. Now this case actually happens pretty often. There's a theorem for this, and it's in your textbook as well, but here's the theorem. If absolute value of r, and we'll discuss what r is in a moment, is less than 0, then the limit, keep running LIN instead of LIM, for n approaching infinity, for the function r raised to the value of n, will always equal 0. So basically whenever your constant here, this value, is less than 0, and that's the absolute value of it, of course, you will always get this value equaling 0 as you're approaching infinity. Alright, now let's look at another problem. For this next problem, for example 2, we're going to be looking at as x approaches infinity for this -2 raised to the x. So take a moment to attempt this, but before you do, I want to note, remember, that this negative is outside what's actually being raised. So be careful what your values will be as you start plugging in and start thinking about how infinity, as x approaches infinity, would treat this function and what the output would be. Alright, so with this, I'd simply state, it's actually pretty simple to kind of think about this, is if you think about as you plug in values for -2, let's say, I'm just going to start plugging random values, let's say 10, let's say -2, 220, let's say -2, 100, let's say -2, 1000, right? And I can plug in various increasing values for x. But the big thing to note is that what do all these values give you? Some larger, I know this is very mathy, some larger negative value. Put a little exclamation point. So as x is increasing, your 2 is just going to multiply itself over and over and over, creating a large value, but it's still always going to be negative. So that means that in this case, you're going to get this answer as the limit approaches of x goes to infinity for a -2 raised to the x, you're going to get a value of -infinity. Oh, I keep doing that infinity sign. There we go. So that is your value for this question. You're going to get -infinity. So it doesn't have to be some finite number. As I said before, infinity is a concept, not a number. We actually typically say that this converges. So this limit is converging towards negative infinity. Now let's do another practice problem. So we'll go to example 3. So here, for example 3, I wanted you to take a moment and see how you would handle this question, which is referring to the limit as c approaches infinity for the function of sine of c. So what is the value of this function as c approaches infinity? So take a moment and try this question. Now my approach might be a bit different from yours, but I would actually probably start off by just simply graphing this or sketching this function. So a sine curve, if we're familiar, looks something like this, and so on and so forth. It actually oscillates between these two values of 1 and negative 1. And since this is the base function, there's no change in amplitude, it would consistently always be negative 1 and 1. And remember that this axis here is f of, well, c, and this is the c axis. So as c approaches infinity, it's actually having an output, f of c, that is divergent. So f of c is divergent. So we have this idea of convergent and divergent, and what divergent means is that make it say, no limit. Thank you for that, Usher. Yes, you are correct. That means that divergent means no limit. So the definition of divergence as x approaches some value n, there's no consistency between the values as it gets towards the end, because notice in this case it oscillates between 1 and negative 1 and along with other numbers, so there is no limit. Now instead of writing this over and over and over, we can actually simply say
limits. Why couldn't I remember anything about limits? Limits. That was the week Aaron got his haircut. Oh God, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist!
Thank you, Lindsay. You are correct. We would simply say that limit does not exist, or you can rewrite it as DNE. I hope you've enjoyed today's class, and I'll see you all next time.